Thank you. So I'm happy to be the last speaker. I will present you two dynamics that can achieve neural networks. So you take a simple neural network and you can actually train it in two different ways. Either you train it in the feature training regime, in which this network will be able to learn features, or you can train it in a lazy training regime, in which it will not learn any feature, and actually it will behave as its first order approximation. So the network is a function of all its parameters, W, and its input X. And here I do a Taylor expansion around the initialization. And in this regime, this Taylor expansion describes well the behavior of the network. And I will show you that there is a characteristic training time below which the network behaves linearly, and after this training time, it starts to behave non-linearly. And there is a very simple trick to force the network to stay in the linear regime, so to stay in the lazy regime. Or if you want, you can also force the network to leave this lazy regime and hopefully learn interesting features. So I will place myself in the overparametrization regime because practically it's performed better in overparametrization regime. And hopefully it's also theoretically more tractable, this regime. And there is actually, in the literature, there is two limits that has been shown when you take the width of the network and you would put it to infinity. So I will present you these two limits. And to understand these two limits, we can understand the difference of these two limits in the context of the central limit theorem. So what is the central limit theorem? You have a large number of random variables, and if you take the average of all these random variables, you get a new random variable. Its mean is equal to the expectation value of the random variable, and its variance is equal to 1 over n, the variance of the random variable. It's like the blue distribution. So when n becomes large, it's more and more peaked, and the expectation value is aligned with the expectation value of the initial random variable. But now if you put 1 over square root of n, when you do the sum, you are in another context in which the variance stays the same. So the variance of the green is the same as the original variance. But now the expectation value will move. The expectation value will be equal to square root of n, the expectation value of the random variable. So the first limit is in this particular setting. So you initialize your weights with Gaussians of variance 1, and for each layer, you do the ponderated sum with the weights, and you divide by 1 over square root of n. And you are in the case when the variance stays the same, but the average in this case is 0 because the expectation value of W is 0. In this setting, once you initialize your network, the output is a Gaussian process. And also in these settings, because of this property, that if you change a little bit, if you correlate a little bit these variables, it will affect a lot the expectation value. If you have small correlation, they will quickly add up and they will quickly change the output. So, and this is more and more true when n become large. So when you take large n, you can approximate this network by its first derivative. So here I have a sketch to visualize this. So we are in the space of all the possible function from the input to the output. So I consider here x to be in Rd and the output being just R. The space of all possible function is an infinite dimensional space. And you consider your network. Your network is just a point in this space, initialized at W0. Now what's happened if you change the value of your parameters? You can move along a manifold. And this is the manifold of your network. And I did a simple experiment just to see how it looks like. It's just beautiful. It's not very. So I just took the three axes here. F of x1, f of x2, and f of x3 are just vary three direction in the input space, and to plot this manifold, I choose just randomly two directions in the space of parameters, and it draws this manifold. It's very funny because it's a manifold that is very cutting itself in pieces. So now let's consider the tangent space of this manifold. We can write it as f of W0 plus the gradient of f with respect to its parameters evaluated in W0 times a small change. And
it really cuts itself?
Yeah, apparently.
So it's not a manifold. It does that?
Maybe it's because I only show three components here, but yes, it does that in.
If it's a projection, of course, it cuts itself.
In the projection, it cuts itself, yes. And this manifold is of dimension, I call it big N, the number of parameters. And now, if you are in the overparametrization regime, what happens is that you have less data in your training set than parameters. And each data during training, each data will push your parameters in certain directions. And during training, you will only evolve in a space that is even smaller than the tangent space. And this space is described by the kernel called neural tangent kernel. And the expression of this kernel is as follows. So it's a function of three parameters, the parameters of the weights of the neural networks, and two inputs, and it's the scalar products of the gradient evaluated in x1 and x2. And as Stefan already said, it has been shown that it's independent of the initialization when, for me n is the number of neurons per layers. So when n goes to infinity, it becomes independent of the particular initialization. It converges to something finite. And also during the training, it does not evolve, so we stay in the tangent space, in this kernel space, which is a subset of the tangent space. And because we are in the tangent space, the weights do not change a lot, but as well the pre-activation do not change a lot. This is the scalings, but when n goes to infinity, it goes to 0. So in these settings, we cannot have features that are learned. Because to have features that are learned, you need the pre-activation to learn to be sensitive to particular inputs. Then there is another limit that has been presented by Lenaik, Shiza. And this other limit has been studied theoretically for one hidden layer network. And the only difference between the two settings, except the number of layers, is that at the output, instead of dividing by 1 over square root of n, here it's divided by n. And this difference, if you look through the central limit theorem, it makes the average, no, the average is 0, yes, but it makes the standard deviation going to 0 as n grows. So when n goes to infinity, at initialization, this network is the function 0 for any instance. And the only way you can change the output is by really evolving the distribution of the weights. So because we have this sum, we can replace the sum by an integral. We can approximate the sum by an integral. Yep, this approximation becomes true when n is large. And we can parameterize the weights by a distribution. So this is really the same. I just replaced the sum by an integral. And for the initial density, we have 0 as a function. And this density has really to change to have a non-zero prediction. And it has been shown by several people that for gradient descent, this density follows a differential equation. And as I said, in these settings, we can have feature learning. I don't say that these features are interesting feature for generalization, but at least since the pre-activation do have to change, we have the hope that they can change and learn some features. So the difference between the two limits are this scaling at the output. Yeah. So now I will make experiments at finite number of neurons. And a priori, we don't know which limit describes better neural networks that have a finite number of neurons.
And why not anything in between?
And why not anything in between? Exactly. To have something in between, we add a parameter, alpha. And by varying this parameter alpha, we can go from one limit to the other and see what happens in between. And so we just multiply the output by alpha. Now, since we choose to keep the square root of n below, if alpha is fixed, constant, and we push n to infinity, we go to the kernel limit. And if, in the contrary, we make alpha behaving as 1 over square root of n while taking n to infinity, we will tend to the mean field limit. But in between the two, we will do experiment to see what happens. In order to have the output of the network in order to have the network that always behave linearly for any width when alpha is large, we do this following trick. We subtract the initialization. So this is our model that we will train. Instead of simply training f, we train alpha times f minus f evaluated at initialization. So this doesn't move, this is fixed during training. It's w at initialization, and we train w. So this is the model we consider. So one over square root of n everywhere, add the output as well. All the weights are initialized with Gaussian with variance 1. And this is our loss, sum over all the training sets, the loss per sample. And here our model is the following one. We have this parameter alpha. We subtract the two f. And we just put an alpha square here. This will just scale the notion of time because it changed nothing for the dynamics really. By putting alpha square here, it makes that in the lazy regime, the time of convergence is constant, does not depend on alpha. We take continuous dynamics. I mean, at least we approximate it numerically. To do so, we use the following trick. We compute the difference at each step because we have to discretize. At each step, we compare the gradients of the previous steps and the current steps. And if the gradient, the angle between the gradient changes too much, we go back and we take a smaller step such that the gradients between two steps are close together to ensure that we are really in the continuous gradient flow dynamics. What slide is here? Okay. Okay, this is detail. So these are the first result. So this is for MNIST with parity. MNIST, so we want to predict the parity of the number with 3 hidden layers, soft plus, and some momentum in the gradient flow. There's no stochasticity. It's not stochastic gradient descent. It's just gradient flow. And this is what we get. It's not really. I mean, I don't know why it does that, but what we see is that at some point we reach a plateau. So we vary alpha, and when alpha is large, maybe I should show here. When alpha is large, f does not have to change much to have the red term to be of order 1. If f just changed by a little, since it's multiplied by this large alpha, the red term will be of order 1.
When alpha was 1, it was the lazy regime and 1 over square root 10. I forgot what.
When alpha is fixed constant, yes, if alpha is fixed constant and you take n to infinity, you reach the kernel limit. If you take a smaller alpha, you will go to the mean field limit. So yes, when alpha is large enough, you reach this lazy regime. This is for fixed.
For you to the kernel.
The kernel. Yes, the kernel regime. Lazy regime.
So how much was n here? Where is the small? What is 1 over root n here?
N is 100 here. So
1 over root 10 is 10 to the minus 1.
yes.
So what happens there is even beyond, what's on the left is even beyond the mean field.
Yeah, I mean, we have to see how it changes when we change n. Yeah, but because these limits, mean field limit and kernel limit, they are limits. It's only when you take n to infinity.
understand what is the main message, because it doesn't mean that kernels simply do not work well. Because if I'm looking at this plot, so as Gerard said, when you go to very, very small alphas, which do not correspond even to the midfield, you get gradually better results, then it goes back up, and then it settles on.
Yeah, so I don't have any general conclusion for which one is better than the other. I will show you different data sets and so on.
So the test errors are fairly small. I mean, the changes are not...
No, exactly. Yeah, exactly. So, what is interesting for me is more when it change, and that for some network one is better than the other, but how much it's changed, exactly what's happened in this regime, I don't have any conclusion. So first I will look at when the transition appears, and then I will show you different architectures, just to another architecture and different data sets. So here what I add here is that I added the ensemble average in dashed line, and what is funny now is that actually there is for the ensemble average, actually for these particular settings, the lazy regime perform better than the feature training, which is the contrary for one-shot training. It means that there is more variance in this regime than in this regime, which is a bit surprising. But what I just want I want you to observe in this plot is that these three lines do not overlap, which means that maybe alpha is not the good scaling to see when the transition appears. What the heck? Oh yes. Okay, this is just so if instead of scaling plotting with respect to alpha, I plot with respect to square root of n alpha, this curve overlap a little bit better already. So it's a clue that this is the correct parameter to tell when we are in one regime or the other. And also we have the same clue when we plot the change of the kernel, because the kernel we can compute it at initialization, but we can also compute the kernel at the end of the training, and we can measure the distance between these two kernels, the initial and the final kernel, and we can do that by varying alpha. And we see that it's smaller and smaller because the network evolves less and less. And these two regimes, two slopes, two different slopes. And when it's below 1, it means that the kernel changes less than its own amplitude. So it starts to be linear. And the only difference between these two plots is the x-axis. And when we put square root of n alpha, everything collapses. So it's again a clue that it's the good scaling. So according to this clue, this is our phase space. We have the number of neurons per layer. And here we have the parameter alpha. And we have a curve. This is 1 over square root of n. And if we are below 1 over square root of n for the parameter alpha, we are in the feature training regime. And if we are above, we are in the lazy regime. If we go to the right, horizontally, we go to the kernel limit. And if you go to the right by going a bit down, by staying below this line, we reach the mean field limit.
You reach what?
The mean field limit. Here I just changed the data set. On the left, it's what you already saw, it's MNIST. And on the right, it's 10 PCA of MNIST. Surprisingly, if we take only the 10 component of the PCA of MNIST, it works better in the feature regime than in a lazy regime. Just a funny fact. These are two other data sets, EMNIST, which are letters instead of numbers, and Fashion MNIST, which are images of clothes. In both cases, it's the lazy regime that performs better. And finally, we did one experiment only, unfortunately, with CIFAR 10. And in this case, we took different dynamics because it's too heavy to train with with gradient descent. So in this setting, we see that the feature learning perform a bit better than the lazy regime. But again, as you observe, the change is not very dramatic. But what it tells us is that it depends on both the data set and the architecture which regime perform better for the generalization. What is very funny to observe is the learning curves. So this is for three different numbers of neurons per layer. This is a big network and a small network. And I plot the loss with respect to the time. And since I do a gradient flow, the time is well defined. And these are different trainings for different values of alpha. And what you can observe is that when alpha is large, when we are in the lazy regime, all the red curves, they overlap here. And there's no, they overlap both with n and with alpha. I mean, they are all overlap, and there's no offset between these three parameters, these three curves. And what is surprising is that, in the contrary, when we are at small value of alpha in the feature regime, the learning curve have a very abrupt behavior. So the loss is almost constant up to one particular time, and it goes to zero very quickly.
The time is 10 to the minus 9.
Yeah, because alpha is super large here, super small here. Yeah. So we really need this dynamic that adapts the time step, otherwise we cannot do that. But what is interesting is that it looks like there is a very characteristic time. And actually, if we rescale the x-axis, if we rescale the time by square root of n alpha, we obtain the following. So it's exactly the same curves. I only changed the x-axis. So all the purple curves, they all collapse together. And the red curves that are in front here, they go here, because I divided by alpha. Because each curve is for a different alpha. And here we see again that there is an overlap of all the curves when alpha is super small. So it means that we have a characteristic time, we call it T1, and this time scales as square root of n alpha. The interpretation of this time T1, again, if we go in this cartoon of the space of function. It's the characteristic time after which we start to feel, after which we exit the tangent space. We start to feel the curvature of the manifold of the network. So and the analogy is that if you take a car and you drive at a certain velocity in a straight line on a planet that has a certain radius, after a characteristic time, you will feel that this planet has a certain radius, that it's curved. This slide is for an argument, a theoretical argument to show that T1 scale has quote of n alpha. It's actually very simple to see this. So it's the time after which we are not anymore in the tangent space. So it means that the parameters did change significantly, or as well as the pre-activation changed significantly. So the parameters and the activation at initialization, they are of order 1. So if we can compute the velocity of the parameters and the velocity of the pre-activation, we can say after what time they will change by a magnitude proportional to themselves. And just to consider here for simplicity the case of the last weights, what is the velocity of the last weights? By gradient descent, it's simply the derivative of the loss with respect to the weights. And if I show you the loss, here, if I derive the loss with respect to the last weights, what I get, so I have to derive this with respect to these weights that are here in this function. There's a factor alpha that will go out and cancel one of these 2 alpha. So I will keep a 1 over alpha. And for n, there's this square root of n that will go out. So I will have a 1 over square root of n alpha. So it means that this is an upper bound because I just consider 1 weight. If there's other weights that are faster, T1 will be smaller, but T1 cannot be larger than square root of n alpha. Actually, it's correct. If you compute the velocities of the other quantities in the network, there's nothing faster than the output weights. The pre-activation have the same velocity, the input weights as well. It's just the weights in the middle, they are a bit slower. Their velocity scales as 1 over alpha n. And now, let me look at an argument for the other time, the time of convergence when alpha is super large. So we are in the limit where the network is linear, and we can compute, approximate this time by just computing the velocity of the output. So the velocity of the output by the chain rule, it's the derivative of the output with respect to the weights times the velocity of the weights. The velocity of the weights is equal to the derivative of the loss function by gradient descent. So here I just replaced W dot by the derivative of the loss. And now we can again do the chain rule. The gradient of the loss is the derivative of the loss with respect to f times the gradient of f. And if we compute the derivative of the loss with respect to f, there's a factor alpha that goes out. So we get 1 over alpha, and we get the gradient of f times the other gradient of f, which is proportional to the kernel. So it means that to fit the training set, we need the red term to be of order 1. So we need alpha times f dot times the typical time of training to be of order 1. Which means that if we replace f dot by this quantity, we have the typical time of training that is of order the inverse of the kernel. And it has been shown that the kernel, I mean, obviously the kernel do not depend on alpha, because it's just the gradient of f times the gradient of f. And it has been shown that it does not depend on n, the number of neurons. So this characteristic time is a big O of 1. It does not depend on alpha and does not depend on n. So we have these two characteristic time, T1 and T lazy. This is the time you have to evolve such that you exit the tangent space. And this is the time you have to evolve to fit your training set, supposing that you stay in the tangent space. So it means that when these two times are equal, you cannot stay in the tangent space and fit your training set. So it gives us the scaling of the transition between the two regimes, alpha star.
But 1 over square root n corresponds exactly to the mean field case, right?
Exactly to the yes. So the transition between the two is exactly at this setting.
Everything is like lazy before.
Yes, exactly.
And then it is mean field.
Exactly. Okay, this slide is just to tell you that the trick I did of doing f minus fw0, if we don't do this trick and we consider large n, the two important results I have that are alpha star and T1, they stay the same because since alpha star goes as 1 over square root of n, this term, when n is large, is negligible. That's it. And yes, this is the conclusion slide. So above this line, we're in the lazy training regime. And we...
so that's what you are saying, in fact.
Exactly.
You're above, you're always lazy. And
And the dynamic stops before this characteristic time T1. And below this line, the dynamics goes beyond the characteristic time T1. The characteristic time T1 scales like that. That's it.